Welcome back, geometry students. We're going to move forward on our unit on triangles, and today we get to cover isosceles and equilateral triangles. Hopefully you heard how I pronounced that. Isosceles and equilateral triangles. Yay! Hooray! So let's start talking about what we're going to cover today. We're getting into isosceles and equilateral triangles, so we're going to cover some theorems. We're going to use theorems in proofs. That's right, more proofs. Woo! We're going to get some algebra applications to this bad boy, and then we'll work backwards to find some angle measures. So that's the plan. How are we going to do this? Well, we're going to get started with notes. Yay, notes. So we're going to talk about some isosceles triangle theorems, and I'll give you a little explanation of how it works, and then what we can use in proof. So the first theorem is here. If two sides of a triangle are congruent, then the angles opposite those sides are also congruent. So if we have two sides of a triangle that are congruent, by default, the angles opposite those sides are congruent. That is an isosceles triangle theorem. And so if you ever use that in a proof, you can totally say, well, that's the definition of isosceles triangle. You can say that. Another theorem is the converse of that, which reads that, well, if two angles of a triangle are congruent, of the same triangle, then the sides opposite those angles are congruent. Okay, and that is also the definition of an isosceles triangle. So you can start with the foundation of these two notes. But even before then, if we may, let's talk about what in the world is an isosceles triangle. So the way an isosceles triangle works looks something like this. Okay, well, clearly we know we have congruent sides and congruent base angles, the angles opposite those sides. But we should know some vocabulary. So basically, for an isosceles triangle, we have two sides and a base. That's helpful. And we have a vertex angle and two base angles. And so when we're talking about isosceles, make sure that we have understood some of that background information. Okay, so if we're dealing with that, and then we have these two notes. Okay, so if we have two congruent sides, then the opposite angles are congruent. And if we have two congruent angles, then the opposite sides are congruent. How can we tell that definition of isosceles triangle? But wait, there's more. Yay, more notes. So now we start talking about something a little bit more complicated, which is really awesome. I find this note particularly amazing. Did you know that if a line bisects the vertex angle, remember the vertex angle? If a line bisects the vertex angle, then that line is the perpendicular bisector of the base. Perpendicular bisector of the base. Now, what does that mean? That means it intersects the base at a 90-degree angle and it cuts the base in half. Okay, so if we have an angle bisector of the vertex angle, that means that bisector is the perpendicular bisector of the base, thus cutting it in half and establishing right angles where it intersects. So if we ever encounter this in a proof, here's some proof reasons that we can use, that the angle bisector of the vertex angle of an isosceles triangle is the perpendicular bisector of the base. So if we're ever proving that we're going to have 90-degree angles there, or we're going to prove that we have congruent sides there, if we ever prove a thing, we can use this argument that the angle bisector of the vertex angle is the perpendicular bisector of the base. On the flippity-dip side, that if we have congruent segments here, and we know that it's a 90-degree angle, we can then establish that those angles are congruent. How do we know? Because the perpendicular bisector of the base is an isosceles triangle is the angle bisector of the vertex angle. So it's just helpful knowledge in case we're ever going to prove a thing, and we just might. We just might. Now wait, the notes aren't done, because we're talking about equilateral now. So now we start talking about equilateral stuff. If a triangle is equilateral, then the triangle is equiangular. What is that word? All right, so let's do a little bit of English lesson. Note, equi means the same, right? Equal, equality, equitable. Equi or equi means the same. Lateral means side, so equilateral, all the sides are the same. Angular, of course, we're talking about the angles, so it means all the angles are the same. So if a triangle is equilateral, then the triangle is equiangular. And corollary, if a triangle is equiangular, then the triangle is equilateral. Okay, so those are a couple things that we can also have a note for. Now, if we ever come across this in a proof, the reason we would use, well, that's the definition of an equilateral triangle. Now, mini quiz. Think about an equilateral triangle. If all equilateral triangles are also equiangular, mini quiz. What would the angle measure of each interior angle of the equilateral triangle be? Now remember, they're all the same, right? So if they're all the same and all of them add to 180, right? That means x plus x equals 180, or 3x equals 180, or x equals 60 degrees. Isn't that a helpful piece of information? That is so useful. So each measure of an equilateral triangle, each angle measure, interior angle measure, is 60 degrees of an equilateral triangle. So these are all the notes, right? Pause, rewind, stop, write this stuff down, because we are so going to use this information right about now. So let's go over a couple of things. Take a look at this diagram here. We've got this diagram. We're going to use an isosceles triangle theorem here. And the question is simple. Is segment AB congruent to segment CD? Let's explain. Well, first let's find out where in the world is segment AB. So segment AB is all the way there, and segment CB is all the way there. Can we establish that they are congruent? Well, I don't know. What do we know? Take a look at angle A and take a look at angle C. Angle A is congruent to angle C, right? So what do we know? If the two base angles are congruent, then the sides opposite are congruent. Okay, so that was that first thing that we talked about. If the two base angles are congruent, then the opposite sides are congruent. So if the two angles are congruent, then the sides opposite them are congruent. So if we have these angles that are congruent, well, then we know the sides opposite them are congruent. So what is the side opposite of angle A? So the side opposite of angle A is actually segment CB. Okay? And the side opposite of angle C is going to be segment AB. Well, that's pretty convenient. So we know they are congruent. And how do we know? How do we explain that? Well, that is the definition of an isosceles triangle. Okay, so definition of isosceles triangle. That's how we know. Okay, so that's how we can explain that one. Next question. Take a look at this next question. Is angle A congruent to angle DEA? Let's explain. So here's angle A down here. And where is angle DEA? DEA is here. Are they congruent? And that's the question. The answer, of course, is yes. How do we know? Because we know by the diagram, that AD is congruent to ED, and that is given by the diagram, right? So there's one tick mark there. They're totally congruent. If those are congruent, then the angles opposite them are congruent. Okay, so what's the angle opposite of AD? Okay, so the angle opposite of AD is angle E, true, or angle DEA, as the case may be. And then the angle opposite of ED, angle opposite of that, is angle A. How cool is that? So now we have those two angles congruent. And guess what? That's what the question's asking. Are they congruent? Yeah, they are. Explain. Again, definition of isosceles triangle. So we can use that to help us come up to some conclusions, right? So we can totally use these notes to help us understand. Let's understand some more. So here's another diagram, a little crazier, and hopefully you can see all the tick marks and whatnot. Here's the first question. Is angle WVS congruent to angle S? Well, there's a lot more going on in this picture. Let's figure out what's happening. Where's WVS? WVS. Okay, so this angle right there. Is it congruent to angle S? Yes. Yes, it is. How do we know? Because that's the definition of an isosceles triangle. Okay, so again, definition of isosceles triangle. They are congruent because if the sides are congruent, then the angles opposite them are congruent. So if you look at WS and WV, they're congruent. So yeah, angle S is totally congruent to WVS. Okay? Next. Now, is segment TR congruent to segment TS? Well, let's take a look. Where is segment TR? Oh, the big triangle. and segment TS. The big triangle. So are they congruent? Well, here's what we know. Now that we know that angle S is congruent to angle WVS, look at what we were given. Angle R and WVS were congruent, that was given. So what do we now know? Transitive property that angle R is congruent to angle S. Okay, that's transitive property, some work right there. Okay, so you can say transitive property of congruence. Okay. Transitive property of congruence, angle R is congruent to angle S. Therefore, by again, definition of isosceles triangle, the opposite sides are congruent. Okay, so the sides opposite are congruent. So now we know totally TR is congruent to TS. And how do we know? Again, definition of isosceles triangles. Okay, so we can now defend because we're seeing what things are happening. Okay, so R is congruent to WVS. WVS is congruent to S. Therefore, R is congruent to S, transitive property. And if those two are congruent, the sides opposite are congruent, definition of isosceles triangle. And that's how we can use those theorems. Okay, so we're building our argument database. You know, how many more things can we argue? So now let's talk about some algebra, shall we? Yay, algebra! Take a look at this diagram. The question is, what is the value of x? We've got to figure out what's going on with this x. So let's take a look at what's happening with the triangle to begin with. We have a 54-degree measure here. Here's x tucked in that little angle measure here. Well, we have these two angles are congruent to one another, and these two sides are congruent to one another. So what do we know? If we know these two sides are congruent to one another, we know the two angles opposite are congruent to one another, right? So now we know that the other angle down here is 54 degrees. Okay? And now let's take a look at the big triangle. So let's operate under triangle ABC. We're going to operate in the big triangle, triangle ABC, the big triangle. We have two angle measures of 54, right? So 54, 54, and something. We don't know what that third angle measure is. We'll figure it out quickly because 54 and 54 is 108, right? And then if we subtract 108 from the big triangle angle measure of 180, we will have 72 degrees. Okay, so we know that this big angle here is 72 degrees. That's the big angle. It's 72 degrees, right? So if the big angle is 72 degrees, what is half of that? Right? We're going to divide that by 2. How do we know it's half? Because these two angles are congruent. And that's what our x is. Okay, so we can cut that in half. So 72 divided by 2 is 36, right? So we now know that the degree measure of x is 36. Okay, so 2x is 72, therefore x is 36. And that's how we get the degree measure for x, which is 36. So that is the value of x. So that's how we can figure that out. But here's something interesting. Why stop there? What more can be said about this diagram? So why stop there? I want to start talking about a thing called solving a triangle. And what we're going to do is see if we can solve this triangle. Let's figure out as much as we can about the sides and the angle measures of this particular triangle. So what we've currently done is we have solved for x. We found x to be 36 degrees. We know the other angle measure is 54 degrees because the sides are congruent. What else do we know? Can we say anything about the segments AD and CD? So take a look at AD and CD. Can we say anything about them? And the answer is yes. Yes, we can. What can we say about them? They are congruent. And how do we know? Do you remember the note that we talked about earlier having to do with perpendicular bisector? If a line bisects the vertex angle of an isosceles triangle, then it's also the perpendicular bisector of the base. Okay, so it's the angle bisector. How do we know it's the angle bisector of the vertex angle? Because look, those are congruent angles. DB is the bisector of angle B. Okay, so DB bisects angle B, and so now we know it is the perpendicular bisector of AC. So that means that AD, because it's bisector. It means AD and DC are congruent. You know what else it tells us? It tells us something more. It tells us that, well, take a look at angle ADB. ADB, you know what we know about angle ADB? It's a right angle. Yep, it's a right angle. That's perpendicular. Definition of perpendicular. It's a right angle. Same thing holds for angle CDB. That also is a right angle. So we can solve a lot of things about this triangle just by knowing a few things. And so I like to talk about solving a triangle because there's so much you can tell. Even though the question was only about solve for x, we can tell more things. You know, we can tell a whole lot of stuff. Those are congruent angles, therefore DB is the bisector. And if it's the angle bisector of the vertex angle, it's the perpendicular bisector of the base. Okay, that's that note. Anyway, yay algebra. Hooray. Let's do another. Or yay algebra. Look at this question. This question, again, very simple. We're going to solve for x. Solve for x. Now, what's going on? We're going to assume that 3x plus 28 is this angle down here, and then 5x is this angle here. So we're going to make that assumption, but then we can totally solve for x because, check it out. We have a congruent side here, congruent side here. If we look at the big triangle, we know that these two angles are congruent. So we know that 5x will be equal to 3x plus 28. And we know that because that is, again, the definition of isosceles triangle. If the two sides are congruent, then the angles opposite are congruent. We don't need to worry about that thing in the middle. We don't need to worry about the thing in the middle because we're dealing with one big triangle. Once we have that, algebra. Subtract 3x from both sides. Then we know that 2x is equal to 28. And then we divide by 2. And then we know x is equal to 14, right? So x is equal to 14. We have solved for x. Ta-da! And we can tell all sorts of things from that. If we know x is 14, we know the measurement of the angle is 5 times 14, or 70. And we know these two measures are 70, right? So that's 140. We know this vertex angle is 40 degrees. We know all sorts of things, okay? So that's super helpful, but yay, algebra. And we can solve all that stuff that we want to. Hooray! Moving on. More stuff. So now, take a look at this picture. What do you think we're getting into? We're getting into equilateral triangles. You remember that mini quiz I gave at the beginning when we talked about notes? Remember that? What is the angle measure of each interior angle of an equilateral triangle? 60. That's coming back right here. Take a look. Okay, so what are the measures of angle A, angle B, and angle ADC? Well, where are these angles we speak of? Here's angle A. Here's angle B, and where's ADC? Ah, here's ADC way up there. Okay, we got to figure out what are those angle measures. Let's take a look. Take a look. Take a look at each individual triangle, right? Just look at ADE. What do we know? We know all three sides are the same. And if all three sides are the same, all three angles are the same. So that is equilateral and equiangular. Remember that word? That's such a cool word. Equilateral and equiangular. So if all the angles are the same, that means they all must be 60 degrees. So in every little vertex here, we got a 60 degrees. 60 there, 60 degrees there, 60 degrees there, 60 degrees there, and 60 degrees there. You know what I'm saying, right? You better know what I'm saying. Look at all these 60s everywhere. That's what equilateral means, right? It's all 60 degrees. So now we can easily answer the question. Angle A, 60 degrees. Angle B, guess what? 60 degrees. Angle ADC, guess what? ADC, 60 and 60, 120 degrees. Ah, right? Don't get cocky. You can't go blind on me, right? So that's how we can find angle measures there. Okay, we know if the sides are all the same, the angles are all the same. Cool? Cool. Next. This is a fun question because you can't assume equilateral, right? Suppose the triangles at the right are isosceles triangles. Ah, I'm only giving you two sides now. Where angle ADE, where's angle ADE? Okay. Angle DEC, okay. And angle ECB, okay. Are vertex angles. Okay, so they're all vertex angles. If the vertex angles each have a measure of 58, so this is what the problem is giving us now. The problem is giving us vertex angles. 58, 58, 58, right? So that's what the problem is giving us. the question then is, well then, what is the measure of angle A and the measure of angle BCD? This one, right? Okay. So now, here's the neat trick. Yay, algebra. If we know that each triangle has a total interior angle measure of 180, and we know that each triangle has a vertex angle of 58, and we know that the other two base angles have the same measure, definition of equilateral, we can save up this neat little equation, right? So we can just subtract 58 and divide by 2 from 180. That's exactly what we will do. But that's what the equation states, right? So if we have that 58 given vertex angle, we know these two are the same, so we can just simply subtract 58 from both sides, or you can do this mentally, it's okay. Subtract 58 from both sides, we have 2x equaling 22, therefore x equals 11, right? So you can do the same thing, okay? So that's a 122, by the way. And that's not 11. That's 61. Whoa, that was close. So x equals 61. Whoa. Silly goose. So we know that each angle measure there is 61 degrees. So now we know 61 here, 61 there, 61 here, 61 there, 61 here. All right. Now take a look at this. Remember the equilateral triangle? All equilateral triangles 60 degrees. This one's 2 units shy, so we have to account for the 2 units greater, but divided by 2. So one more on top of 60. Could have done that anyway. You could do this mentally, and it doesn't matter. It doesn't matter how, but you will know that the other angle measures are 61. So if we know that, we now know the answer. Measure of angle A, of course, 61 degrees. What about the measure of angle BCD? Let's be cautious here. BCD is all the way here. So we have 58 and 61, right? That's 119. So you got to be careful there. Okay, so the measure of BCD is 119. So be careful with your algebra. If this went too quick, right, this particular problem, this is a great time to pause and rewind. But let's move on. All right. More angle measures. Take a look at this one. This should be simple now that we know. We're going to find some angle measures. The question is DE congruent to DF? And let's explain. Here's DE, here's DF. Are they congruent? Can we explain that? Well, how in the world are we going to know if they're congruent? That's the question. How will we know if they're congruent? We will know they're congruent if we have angle F as 61, right? So we know if they're congruent if angle F would be 61. Now, if you have short-term memory, meaning you don't remember the problem we just did, we can do some algebra. If you do remember the problem we just did, well, then you know the answer. So, is the measure of angle F 61 degrees? Let's figure that out. So we have 58 and 61. If we add those together and subtract that from 180, we would have our missing measurement. So 58 and 61 happens to be 119. You might be thinking, man, that's a familiar number. I swear, did we just do a problem with that? Ugh, I don't know. Then we subtract 119 from both sides. Guess what we're going to get? 61. So yes, as a matter of fact, angle F is 61. Again, we just did that. So anyway, so the measure of angle F is 61. If they are congruent, right? If 61 is congruent, what does that mean about the opposite sides are congruent? So is DE congruent to DF? Yes. And that's how we would figure that one out, right? So cool. More examples. Cats, I feel like I'm learning. Yay. All right, last one. No pictures. Isosceles triangle XYZ has a base of XY, and a measure of angle Y is 34. What's the measure of angle Z, all right? I don't understand what this question is saying, so you know what I'm going to do? Draw a picture. Ta-da. There, I just drew a picture. So once I draw a picture, I'm all set. Now notice the problem gives me the fact that this is isosceles, right? It gives me isosceles. And if it gives me isosceles, I now know that the measure of angle X is 34 degrees. Now how do I know angle X is the other base angle? Well, because the problem told me that XY is the base, right? So the problem told me XY is the base. I can go ahead and assume that. I got to find the measure of angle Z. So again, add it and subtract from 180. 34 and 34 happens to be 68, right? So 34 plus 34 is 68. All I have to do is subtract that from 180, and I have my vertex angle. Right? So I do some regrouping. Let's see, that's a 1, 1, 2. There it is, 112. Now you can see that this diagram I drew, not very accurate. So the measure of angle Z is equal to 112. Remember the diagram I drew? How can we make it more accurate based off what's there? The triangle, in fact, would look something more like this. That's probably a better diagram, but it doesn't change the numbers. The numbers still change, which is why I say in geometry, never trust your eyesight. Always go by the numbers. It's all about the numbers. Anyway, I hope you learned some stuff about isosceles and equilateral triangles. I hope it was fun. I hope it was easy. If not, pause, rewind. Let's do some practice. I'll see you guys later.